Hello everyone, good evening to all. So in previous lecture we have discussed how to derive Fourier series of any function in an arbitrary interval minus L to plus L, and in this lecture we mainly derive complex form of Fourier series. Okay, as we discuss the Fourier series of any function in a certain range minus pi to plus pi or minus L to plus L can be obtained by taking corresponding sine and cosine series. Okay, that means Fourier series of any function satisfying the Dirichlet condition can be expressed in terms of sine and cosine series. But one thing that have to mark, sine and cosine terms take their exponential or complex form. So as sine and cosine terms take their exponential or complex form, so that's why we can convert a function in Fourier series as complex form. Okay, because if we observe sine function sine theta, that is e upon I theta minus e upon minus I theta whole divided by 2i, and cos theta, that equals to e exponential I theta plus exponential minus I theta divided by 2. Okay, so as sine and cosine takes their exponential form or complex form, so we can convert Fourier series of any function in sine and cosine series as their complex representation. Okay, so in order to derive the complex form of Fourier series, we have to consider a function, suppose f of x, described in a range of minus pi to plus pi, satisfying all the Dirichlet conditions. And if f of x satisfy all the Dirichlet conditions, then we can express f of x in Fourier series as a naught by 2 plus summation n equals to 1 to infinite a n cos nx plus summation n equal to 1 to infinite b n sin nx. Clear? This series has already discussed in your first class. So how the sin nx cos nx takes their exponential form? So cos nx can be written e upon exponential inx plus exponential minus inx whole divided by 2, like sin nx also can be written exponential inx minus exponential minus inx divided by 2i. Okay, so if we use cos nx and sin nx in the series, then the corresponding series changes like a naught by 2 plus summation n tends to 1 to infinite a n e upon inx plus exponential minus inx divided by 2, okay, plus summation n 1 to infinite bn e upon exponential inx minus exponential minus inx divided by 2i. Clear? So if you take or if you observe, there are two equal terms of an and bn that corresponding to inx. Okay, so as inx corresponds to both an and bn, so you can take common here. So a naught by 2 plus summation n. Okay, so first term, that is an, okay, and here the second term, that equals to, so take 1 by 2 common, as 1 by 2 exists in both case, so take 1 by 2 common, 1 by 2 an plus bn by I, okay, plus exponential inx plus summation n raised to 1 to infinity. So also there is a I term, okay, I, that equals to an, that is bn by I e upon minus inx. Clear? Okay, So if you multiply I here and also multiply in the lower part, and in case of e to the power minus inx, so how the change of series takes place? A naught by 2 plus summation n upon 1 to infinite half, that equals to a n, that corresponds to a negative value as I square is minus 1. So that can be written as I bn plus e upon inx plus summation n raised to 1 to infinite 1 by 2 a n, as I square is plus 1, and that will rise I b n e upon minus inx. Clear? Okay. So if we substitute here, if we assume the constant terms a naught by 2, a n, I b n and a n minus I b n is C naught equals to a naught by 2, let C naught equals to a naught by 2, Cn equal to a n 1 by 2, that 1 by 2 that will corresponds to a n minus I b n, okay, and C minus n is 1 by 2 a n plus I b n. Okay, so then the complex Fourier series where a c0, cn and c minus n are called complex Fourier coefficients. Complex Fourier coefficients. So how the Fourier series changes? So Fourier series equals to, that is c naught, okay, a naught by 2, that is c naught plus summation n tends to 1 to infinite, that is Cn e upon inx plus summation n equals to 1 to infinite c minus n e upon minus inx. Okay, and this series is known as Fourier complex series. Okay, we can also reduce the Fourier complex series in the range of minus infinity to plus infinity. How can we write? Okay, this is the one form of Fourier complex series. Now we can change the Fourier series into a minus infinity to plus infinity. So if you observe here, there is the variation of minus n. Here c minus n, but n value varies from 1 to infinite. Okay, and if I take here n varies 1 to infinite, then we can say minus n varies from minus infinity to minus 1. Okay, so if you change the value of n, then how can the series changes? Okay, so this series can be written as f of x equal to, if we replace here as n varies to 1 to infinite and there is c minus n, then we can say if we replace n by minus n, then my limit changes from minus 1 to minus infinity. Okay, so this can be written like n, okay, this term I write this term as first term, n equals to minus 1 to minus infinite Cn e upon inx, okay, by replacing n by minus n. Okay, the limit changes to minus 1 to minus infinity, then come to this term. Okay, this one, that is c0. Okay, c0 I can write here Cn e upon inx. Okay, Cn upon inx at n equals to 0. Okay, I can write this term c0, okay, plus come to this term. Okay, this term there will be no change, n equals to 1 to infinite Cn e upon inx. Okay, so if you observe the variation of n, here variation of n takes from minus infinity to minus 1, and here n equals to 0, and then n equals to 1 to infinite. So I can write here, that is minus infinity to minus 1, then 0, then 1, then infinity. Okay, that is the variation of n. So as a whole, n varies from minus infinity to plus infinity. So this series can be written like f of x equals to summation n tends to minus infinite to plus infinite Cn e upon I n x. Okay, so this is the transformation form of Fourier complex series or Fourier series in exponential form. Okay, but we have to evaluate the Fourier coefficient or complex coefficient Cn. Okay, as C0 is a constant term that takes a0 by 2 value, but we have to evaluate the value of Cn. Okay, Cn and C minus n. Okay, so we can evaluate Cn because C0, Cn and Cn minus n are called Fourier complex coefficients. Okay, so how the Fourier complex coefficient varies? Okay, so let's evaluate Fourier complex coefficients. Okay, so value of Cn that we obtain 1 by 2 an minus ibn. An minus ibn. An and bn are the Fourier coefficient when the function changes from minus pi to plus pi. Okay, so we know the values of an and bn, that is an equals to 1 by pi integration minus pi to plus pi f of x cos nx dx. Clear? Okay, plus minus bn equals to 1 by pi integration minus pi to plus pi f of x sin nx dx. Okay, so if we take the common terms 1 by 2 pi integration minus pi to plus pi f of x, then that will be cos nx minus I sin nx. Cos nx minus I sin nx. Cos nx minus I sin nx, we know that is e to the power inx minus inx. Okay, so 1 by 2 pi integration minus pi to plus pi. Okay, f of x e of exponential minus inx dx. That is the value of Cn. Okay, this is the value of Cn, that is 1 by 2 pi minus pi to plus pi f of x e upon minus inx. Okay, so likewise if we replace n by minus n, then we can replace. So that's why C minus n will take the value 1 by 2 pi integration minus pi to plus pi f of x e raised to I nx dx. Okay, so these are the coefficients of Fourier series in complex form. Okay, so I think you all able to understand what the Fourier complex series says.